All right, so let's finish working some problems from Chapter 3, some example problems. What we are focusing on here in Chapter 3 is we are looking at applying the first law of thermodynamics. We haven't talked yet about properties of substances. So these values that I'll be presenting here in the following problems, don't be too concerned about where these properties come from yet. In the following chapter, I'll tell you where they come from and what they mean. For now, I'll just give you a brief description of these properties and how I came about getting them, and then maybe a little insight into how you would be doing it here in the short future. So in this problem, the first one we're doing, we have a piston. So we have a closed system. And initially, it has a volume of 0.2 meters cubed. So here, I'm looking at this point here. So we have a closed system. Inside this closed system is a saturated liquid refrigerant 134A. So basically, it's a fluid and the state that that fluid is in. We also know what the volume of that fluid or that mass is occupying. And we also know the pressure. So knowing the state or the phase that this fluid is in, knowing the pressure, we could look up in the tables our specific volume, which is given here, and I'll teach you how to do that in a later lecture. But for now, you just take my word for it that the specific volume for this mixture is 0.000845 meters cubed per kilogram. In state 2, so here's state 2 over here. In state 2, we have a condition where we've had a little flame. So I drew a candle there. That candle has added heat to this piston, and it's caused the piston to expand. So we have more volume in our second case than we did in our first case. The temperature has increased to 50 degrees Celsius, and the piston has moved such that the pressure has remained constant from state 1 to state 2. The question in this problem is, let's find the work done in this by the system to the surroundings. So where do we start? Well, what we're going to use is our boundary work definition, and I'm going to write that here. Our boundary work definition states that if we integrate the pressure times the volume from state 1 to state 2, that will give us a value for work. Because remember, work, what we're talking about is a force times a distance. In this particular case, pressure is the same in state 1 as it is in state 2. So pressure comes out of this integral. So if we're integrating a bunch of small differential volumes, what is that going to give us? It's going to give us the change in volume from 0.2 to 0.1. So integrating this, we can obtain pressure, which is constant, times volume 2 minus volume 1. Well, being savvy engineers that we are, we can manipulate this equation so that we can use some of the values that we have already. Remember, since we are saying that this is a closed system, we know that mass is also constant in state 1 and state 2. So we can rewrite this by using the specific volume by factoring out a mass. So we have pressure times mass times the specific volume at state 2 minus the specific volume at state 1. Because specific volume is just volume per unit mass, so I'm factoring out that mass. Well, we know the specific volume at state 2, and we know the specific volume at state 1 is the saturated liquid state of this particular fluid. So now we have the values that we need to solve this problem. What we are lacking is the mass. That's the only unknown, is the mass here. Well, let's solve for that, and let's do that over here. So mass, we could say, and this is the definition that you can use, is just, if we want to find the mass of, and this is the case for a closed system, is the volume of our system at state 1 divided by the specific volume at state 1, or this is also VF. Well, we know that the volume at state 1 before it expands is 0.2 meters cubed, and the volume, the specific volume of this fluid at state 1 is 0.000845 meters cubed per kilogram. So just by looking at the units, we can see that the meters cubed cancel. This kilogram comes up to the numerator, and if we divide these, we would have that this closed system has a constant mass of 236.6 kilograms. So using this, we can solve our problem now. So let's go ahead and plug in our values. Our pressure in both cases is 800 kilopascals. So that's 800,000 pascals. We can multiply that by the mass that we calculated, 236.6 kilograms. And that's all multiplied by the change in the difference in specific volume between the two states. So, carrying all these calculations out, we obtain a value of positive 5,227 kilojoules. Now keep in mind, I divided already this final answer by 1,000. That's why I'm expressing it in kilojoules. Another thing to note is that positive means work is done by the system. So if work is done by the system, we use a positive sign. If we are putting work into the system, so if we have some type of work acting on the system, it would be a negative sign. And we'll be using this sign convention here in the next few examples so we can start practicing, getting used to it here with time. So let's look at our next problem that we can work. Alright, so in this problem we have a candle that's heating another case where we have a closed system, and we have a piston attached to this closed system again. This time it's laying on its side, it's sideways. But we have a fan that we've attached into the system, so we're putting work in to this fan. We're also putting heat in with a flame. We're putting 80 kilojoules of heat. Now what we want to find is what is the work that is done by this system. So basically, is this piston going to move to the left, or is this piston going to move to the right? And if this piston moves to the left, our sign convention would be negative as an end result. If it moves to the right, our sign convention would be positive because it's giving us work, and we could extract work out of this system. So let's look at this. So let's apply the first law of thermodynamics in two ways. The first way that we can apply it is by looking at a system, or the change in energy of a system. So we could say that energy in minus energy out is equal to the change in energy of the system. Remember, we'll be expressing the first law of thermodynamics a few different ways, and I'll practice doing it the other way, and the way that we will be using it throughout the rest of the course. But I thought it'd be a good practice to use it this way one time. So if we look at how much energy is coming into the system, so let's look at the energy coming in. We have work done by the fan in this system, which is 18.5 kilojoules. We also have work being done by the flame, so it's 80 kilojoules. Let's look at what's coming out of the system. I'm going to guess, so this is a guess. We don't know for sure until we solve this problem and find out that this work from this piston is positive, but I'm going to say that WP is going to be work out. So let's assume that. And the change in energy of a system, keep in mind from our lectures, is going to be the sum of the change in internal energy at the two states, the change in kinetic energy, and the change in potential energy. Well, since this system is not moving, it's fixed, we can neglect our kinetic energy term. Potential energy, we don't see any changes in elevation acting in our system, so we can neglect our potential energy. So we'll only consider internal energies for this problem. So let's go ahead and add some of these terms. So this is 98.5 minus WP equals to, and remember this is caps U, so I'm going to factor out an M. We have 5 kilograms of steam. And using some of the properties that we have of this steam, we could calculate what the internal energies are. Again, that is not the primary focus of this exercise, and I'll be showing you how to do that. For now, take my word for it on the values of these internal energies. So what I've written is mass times U2 minus U1. So solving this, we would get a positive 350 kilojoules. The positive indicates that it's work out, or piston moves to the right. Okay? I'd like to solve this problem one more time using the more conventional means that we'll be solving our problems, and that's using the more conventional way of writing the first law of thermodynamics. So the way we're going to be typically doing it is writing the first law of thermodynamics like this. So what this is saying is essentially the same thing as what we were writing before, except now I've expressed the energy in and energy out in terms of heat and work, since remember that's the types of energy that we're going to be assuming act on our system boundary. We also have the change of energy that's occurring inside of our system, which is taken into account by the internal energy, the kinetic and potential energies. We've already determined that kinetic and potential energies we can neglect. And if we look at our sign convention, we can say that 80 kilojoules of heat added to our system, when we add heat transfer or heat to our system, we'll assume that is positive. So I'll write this as 80. When we have work done by our system, we'll assume that that work is negative. So it's 80 kilojoules minus a negative 18.5 kilojoules. So keep in mind, whenever we have work done, that we are doing work to the system, we assume that that is negative. All right, do we have any other works that we need to take into account? Yes, the work of the piston. And again, we're assuming that this work of the piston is going to be positive, so we'd have a minus work of the piston. And this is equal to the mass times U2 minus U1. All right. So rearranging here, we can show that work from the piston is equal to mass times U1 or minus U2 plus 98.5 kilojoules. And I switched the sign inside of this parentheses, U2 minus U1, because I distributed that negative sign throughout the equation. Plugging in the values here, we would get the same answer. (350 kilojoules). And positive indicates that we are able to, or it's doing work on the surroundings or on the boundary. So those were a couple examples. I'll work another example in the next lecture so we can continue to practice different applications of the first law of thermodynamics.